Moving into 10.8, we're going to be looking at Taylor series. Taylor series is just a special example of power series, and really it's the whole purpose of even talking about power series. Taylor series, I think, is the most important thing in Calc 2 that we are going to learn. So before we jump into what a Taylor series is, let's just remember that in the last section, section 7, with power series, we were seeing that a power series, which is a series that has those variables in it, those powers of x, sometimes approaches a function. And what's really nice about that is that that lets us take really complicated functions and write it out as an infinite polynomial. What would be even better, and what Taylor series does, is instead of just hoping that a power series approaches some particular function, let's try to generate a power series given some function. Before we write out the definition for that, we're going to have to do a little bit more work. So let's just suppose that right now we do have a power series that is equal to some function f of x. So f of x is equal to an infinite series. This is going from 0 to infinity. Of our generic power series here. So some constants out in front, and then x minus a to the n. Keep in mind these a's don't really have anything to do with each other. It's just, I don't know, it's just the way the book writes it out. This a is where your power series is centered. It will always converge at this a, and hopefully even a small interval around the a, if not the entire number line. These are just generic coefficients out in front that have to match up to our function f of x. In fact, it's these coefficients, these a sub n's, that we need to find before we can write out the power series for our function. So let's just write out the first few terms here. Of course, the first term would just be the constant a sub 0. If I plug in a to be 1, if I plug in n to be 1, I get a sub 1, and then just x minus a to the 1. Maybe one more term here, a sub 2, x minus a squared. And then there would be an infinite more of these terms here. Okay, what we are going to do is we're going to use one of the last theorems that we saw in the last section, which says that you can take derivatives of these infinite series. So if I take the derivative of the left-hand side here, our function f of x, that's going to be equal to the derivative of my infinite series here, term by term. So if I take the derivative of this term by term, a naught is just a constant, so it goes to 0. The derivative of this with respect to x is just going to bring out that coefficient a sub 1. Plus, if I take the derivative of this next term here, the 2 comes down, a little bit of a chain rule. So the 2 comes down, you still have that constant a sub 2, and now it's just going to be x minus a to the 1 power. Plus, and then just imagine that there's another term here, a sub 3, x minus a cubed. That 3 would come down onto the coefficient a sub 3, and we'd have x minus a, but it wouldn't be cubed anymore. It would just be squared, and then again, there'd be an infinite more of these terms. Okay, so we can even write out what the generic derivative would be. So if I have just this as a sequence terms, a sub n, x minus a to the n, I would just bring down that exponent n onto the coefficient a sub n, and then I would take 1 away from my exponent on the x minus a part. Okay, so just generically, this is what the derivative of my series would be. That's just taking the derivative once. We could keep going. So I'll do these a little bit quicker now. So the second derivative, my a sub 1 this time, would go to 0. Then I would take the derivative of this next term here, which would be that 2 a sub 2. Derivative of this next term, we would bring the 2 of the exponent down and multiply it by that 3. Still have the a sub 3, and that would be x minus a to the 1. Plus, I'll just dot it at this point, and then from here, I already have the n out in front. I'm also going to bring down the exponent n minus 1. I still have the coefficient a sub n, and now it's going to be that x minus a, but this time to the n minus 2 power. Okay, we're going to keep taking the derivative over and over and over again, and eventually we'll get to the nth derivative. So with the nth derivative, I'm going to just kind of dot this a little bit, but we're looking at this term. So if I take this term and I take the derivative n times, my exponent is going to keep coming down and keep coming down and keep coming down, and eventually my n exponent is going to go all the way to 1. So now, just imagine that out in front, we have the n, and it's going to be times n minus 1, and then this next exponent, n minus 2, comes down, and then n minus 3, and n minus 4, and we already know what that is. That's the n factorial. We're still going to have that coefficient a sub n that's always there in this term, but now this x minus a is only going to have an exponent of 0 at this point. Sorry, I was thinking. Because if I take it n times, then my n is going to go all the way down to 0, so that term's basically just going to disappear. So the nth derivative is going to have this n factorial a sub n plus, and then it's going to have some other terms on the n that's not super important. All that matters with this other stuff is that it's stuff with those x minus a terms on the outside. Okay. Now, the last little bit is let's look at all of these different derivatives, but plugging in our center a. So if I take just the original function itself and plug in a into this thing, all of the terms that have x minus a in it are going to go to 0, and all that's going to be left over is that coefficient way in the front, that a sub 0. If I were to plug a into the first derivative, so now we're looking at this line here, if I were to plug a into this, everything that has x minus a goes to 0, but we have this coefficient out in front, a sub 1. If I were to plug a into the second derivative, looking at this line now, everything goes away except for that thing out in front, 2a sub 2. Plus, or not plus, sorry. And then finally, the last thing, let's look at what happens if I plug a into the nth derivative, which is this last term here. All of this stuff with x minus a's goes to 0, but we're going to have that coefficient way in the front, that n factorial a sub n. In fact, this is how we're going to define our a sub n. We can find the a sub n's by taking the nth derivative at a and then dividing over that n factorial. So finally, just repeating what I said there, we can define our a sub n's to be the nth derivative at a divided by n factorial. Remember, the whole point of starting was that if I want my function to be a power series, the only thing I didn't know is I didn't know these coefficients a sub n out in front. But with all this work we just did, we have now solved for them, and we can find them given a function. This lets us now define Taylor series. So definition, Taylor series. And let me write it all out here. So let f be a function with derivatives of all orders. This just means that you can take the derivative over and over and over again without issue throughout some interval containing our centering point a. Then the Taylor series generated by f at x equals a is the following. So it's going to be that infinite series. It is going from, sorry about that. It is going from n equals 0 up to infinity. The coefficients are next. Remember, we are defining our coefficients. I can't use n anymore because n is my index, so the book uses k instead. So we're taking the kth derivative, plugging in my center a, and that's going to be divided by k factorial. That multiplied by our x minus a to the k's. This should be a k out in front as well, sorry. So the series k goes from 0 to infinity of this stuff. And that's pretty much it. So we could write out the terms here, right? The first coefficient, if I plug k to be 1 into all of this, it's just going to be f at a. Or sorry, we're plugging 0 in for the k's, not 1. So this is the 0th derivative, which is just the function itself at a. That's where this f of a is coming from. 0 factorial is 1. And if I plug a into this, of course, that's just going to give us, not plugging a into this, sorry, if we're plugging k to be 0, that's just going to give us 1 here as well. So plugging 0 into my series just gives us the coefficient f of a. If I plug k to be 1, I get the first derivative at a divided by 1 factorial, which is just 1, times x minus a to the 1. If I plug k to be 2, I get the second derivative at a divided by 2 factorial times x minus a squared plus, and then you can just keep going with this. So the third derivative at a divided by 3 factorial, and then x minus a cubed and so on and so forth. One more definition I want to leave you with here before I cut to the next video, and that's something called the Maclaurin series. The Maclaurin series is the same thing as the Taylor series, except it's not centered at A, it's only centered at 0. So I'll just put same as Taylor series, but with A equals to 0. It's just a very special case of the Taylor series. I'm pretty sure that these two people actually came up with this at roughly the same time. And so just to give him a little bit of credit, they named this part of it after him. So this is going to be k, of course, going from 0 to infinity. You're still going to have that f derivative k at 0 now, divided by k factorial. And instead of x minus a's, they're just going to be x to the k's out in front. So just a very simplified version of Taylor series, a more generic, a less generic version, a very specialized version of Taylor series. Okay, in the next video, I'll do an example or two of actually finding Taylor series.